Right, so we are talking about the discrete time Fourier transform, and in particular the properties of discrete time Fourier transform, right? So we talked about shifting in the time domain, shifting in the frequency domain. We talked about differences. We talked about accumulation. We talked about linearity, and perhaps one or two more. What we're going to start with today is differentiation in the frequency domain, and this is very similar to what we did in the continuous time. And it's just actually what happens to the time domain signal if you differentiate in the frequency domain, right? So that's what we're going to try to see. So the question is, okay, if x of n has a Fourier transform which is equal to x of e raised by j omega, right? What is a time domain signal which corresponds to the derivative in the frequency domain, right? So the question is here, what is this equal to, right? And in order to answer this, I can go about the definition. And in particular, if I just start out with the definition, yeah. So the definition of the Fourier transform, right? So the Fourier transform is x of e raised by j omega is equal to summation n going from minus infinity to plus infinity x of n e raised to power minus j omega n, right? So this would be the definition of the Fourier transform. And if I differentiate with respect to omega on both sides, right? So if I differentiate with respect to omega here and differentiate with respect to omega here on the right-hand side, what I get is this derivative can go inside the summation. And so this is the derivative of e raised to power minus j omega n. And this is equal to summation n going from minus infinity to plus infinity, x of n times minus j times n and e raised to power minus j omega n, right? So that's the derivative of the exponential. And then what I obtain is, kg, this is equal to minus j n going from minus infinity to plus infinity n times x of n e raised to power minus j omega n, right? So from here, what I can conclude is, okay, so let me put the j inside so that I can make a point. Right, so this is summation n going from minus infinity to plus infinity, and this is minus j, right? So if I just collect these terms together, and then what I observe is, okay, on the left-hand side, I have something which is a function of frequency, right? So this is, let's say, y of e raised by j omega. And this y of e raised by j omega is actually the Fourier transform of whatever is inside these pink brackets here, which is y of n, right? And consequently, I can conclude that the Fourier transform of minus j times n times x of n is actually equal to the derivative of x of e raised by j omega with respect to omega. And from here, I can also conclude, if I just multiply j with j on both sides, or divide by minus j on both sides, right? That would say the Fourier transform of n times x of n is actually equal to j times d by d omega x of e raised by j omega, right? So this is one of the important properties. It's called the differentiation in the frequency domain property. Any questions that you may have here? Okay, let me apply this property in determining the Fourier transform. So let me put this property up here. right? This is something I know, right? Let's use this uh, for the following example. And the exercise here is, yeah, what is the inverse Fourier transform of 1 upon 1 minus alpha e raised to power minus j omega whole squared, right? So this is something I need to find out, right? And yeah, so I can determine this by the fact that, so let me call this A, right? By the fact that so this is the very first example we did, that A raised to power n times u of n has a Fourier transform given as 1 upon 1 minus a e raised to power minus j omega, right? So in the on the right hand side, I mean the Fourier transform, what I want is a squared in the denominator, and the squared in the denominator I can get by what? By differentiation, right? So, and that plays a part. So let's say uh, n times a raised to power n u of n, that has a Fourier transform which is equal to j times d by d omega of 1 upon 1 minus a e raised to power minus j omega. And all I need to do then is to compute this derivative and see what this derivative turns out to be, right? So this is equal to j times, in the denominator, I have 1 minus a e raised to power minus j omega whole squared. And then I have a minus 1, which is there because the power of 1 minus e raised to power minus j omega was actually minus 1. So minus 1 is there because of that. And then I just need to differentiate. Um, so I use a chain rule of differentiation. I just need to differentiate this with respect to omega, right? So there's a minus sign, which is another minus sign, which is because of this minus sign here, and then a times e raised to power minus j omega times minus j, right? So this is the derivative, a simple derivative with respect to omega, right? And what I get here is, um, so this is minus 1, this is plus 1, and j times j is minus 1, and there's a minus there, so this is a e raised to power minus j omega upon 1 minus a e raised to power minus j omega whole squared. So if there are any questions that you have about how I took this derivative, I think it's simple enough, but if you have questions, so let me know, right? So this is what you have, okay? Which is, okay, I just use the derivative property to conclude that the Fourier transform of n times a raised to power n times u of n is equal to a times e raised to power minus j omega divided by 1 minus a e raised to power minus j omega whole squared. But this is not what I wanted. I mean, what I wanted was, um, I mean, ये चीज़ नहीं होनी चाहिए थी, right? I mean, this should not have been there, right? So how do I get rid of this? I can get rid of this by using the fact that by the shifting property, right? So if I say, if I just shift the time domain by 1, so n plus 1 a raised to power n plus 1 u of n plus 1, the Fourier transform for that is going to be equal to a times e raised to power minus j omega, whatever I had earlier, 1 minus a e raised to power minus j omega whole squared times e raised to power plus j omega. And the e raised to power plus j omega actually cancels with e raised to power minus j omega. I mean, that's actually what I wanted to do, right? And then, so n plus 1 a raised to power n plus 1 divided by a times u of n plus 1. The Fourier transform for this is what I actually wanted, right? So this is 1 upon 1 minus a e raised to 1 minus j omega whole squared, right? So all I've done is the a that I had here, I've just brought it down here. So I've multiplied the time domain and the frequency domain both by 1 upon a, and I can do that because of linearity, right? And then I can simplify this a little bit further. I mean, this n goes away, and this is just a raised per n, right? So this is the answer that I have. And I just, if I play around a little bit intelligently, right? So this signal actually starts at n equals -1, and then there's, or n equal, for values of n which are less than -1, the signal is 0. N equals -1 pe, that's the first time instance at which this unit step is non-zero. And if I just plug in n equals -1, what happens, right? At n equals -1, what happens? And let's say this is, let me call this as x of n. X of -1 is just equal to -1 plus 1 times a raised to power n times u of n plus 1, which is 0, right? So the first value at -1 is still 0. And consequently, I can say the x of n, another way to write x of n would have been this n plus 1 a raised to power n times u of n. And the only way I can do, the reason why I can do that is because I know that n equals -1 पे वैसे ही 0 है, so why not just start the unit step at n equals 0? Okay, so this is the final result that you get. Okay, all right. Any questions here?
एक्सक्यूज मी सर,
जी उमर,
ये टाइम डोमेन में हमारे पास n जो है, मतलब उसको हम किस तरह इंटरप्रेट कर सकते हैं? वो n इज इक्वल टू 1 सेकंड होगा या 1 पाई होगा या?
So Umar, so that's just an integer and that's just an index. Okay, and this n could be really anything in the discrete time domain, right? So this could be, for example, days, right? Okay, the number of confirmed cases per day, right? And then this n is 1, 2, 3, 4, and so on and so forth.
क्या है, पाई हो सकता है?
जी,
पाई हो सकता है?
पाई भी हो सकता है, बट लेकिन
तो
n is
पाई तो
नहीं,
इटसेल्फ इंटीजर नहीं होता ना?
नहीं, n is always an integer. N is always an integer, but the question is, what is the interpretation behind that n, right? And that, as far as this is concerned, because n is an integer, x of n is nothing but an array, right? It's a collection of data, right? Just like you use C++, you're familiar with C++, you're familiar with MATLAB, right? उसके अंदर आपको एक data array में दे दूं आपको, so then that's just an array which is indexed by integers, right? And then you say the first sample is equal to this, the second sample equal to this, the third sample equal to this, and so on and so forth, right?
The samples themselves could be decimal values.
Could be. Yeah, could be. The samples themselves could be. So in other words, x of n could be a real number, right? Just like x of, if I say x of n equals a raised to power n, right? So x of 0 is 1, and let's say 2 raised to half raised to power n again. So x of 1 is 0.5, and 0.5 is not an integer. Is that what you said? Trying to say, Umar, या कुछ और कह रहे थे आप?
मतलब अगर कॉस्ट को हमने प्लॉट करना हो तो वो आप पाई पे उसको सैंपल कर लेंगे तो वो ±1 बन जाएगा। वो आप फिर आप n इज इक्वल टू 1 पे पाई होगा और n इज इक्वल टू 2 पे 2 पाई होगा।
नहीं, so n equal, okay, आप सैम्पलिंग की बात कर रहे हैं, right? So we said this in the beginning as well, कि another way you could do this, obtain a discrete time signal, is through sampling.
Yes sir.
Right? So एक continuous time signal आ रहा है और उसको आप sample कर रहे हैं with a certain sampling frequency, right? So the first sample is at time 0, the second sample is at, let's say, 1 millisecond, the third sample is at 2 milliseconds, and third 3 milliseconds, and so on and so forth. Okay, but like my discrete time उसको represent कैसे करूँगा? मैं कहूँगा the first sample, the second sample, the third sample, the fourth sample, and all I'm going to use is indices. And the back in the implicit एक interpretation है कि यार असल में एक continuous time signal आ रहा था और n equals 0 का मतलब 0 milliseconds है, n equals 1 का मतलब 1 milliseconds है. But as far as all of this mathematics is concerned, this would just account for the fact that n is just an integer, is an index, right? So n is an index, which could be negative,
Okay, sir.
right?
Thank you, sir.
All right. So, let me, any other questions? Right, so what I'm going to do next is the convolution property. I'm going to spend some time on this. This, once again, as in the continuous time, is also an extremely important property. And what it says is, if there's convolution going on in the time domain, as in the continuous time case, the similar thing applies in the discrete time case as well. If there's discrete time convolution going on in the time domain, in the frequency domain, the DTFTs of those two corresponding time domain signals are multiplied, right? So that's the convolution property, right? So in other words, if I say the y of n is x of n convolved with h of n, and let's do a proof for this as well, right? So if y of n equals x of n convolved with h of n, what that means is I just apply the definition of convolution. This is in k going from minus infinity to plus infinity. This is x of k, and this is h of n minus k. And I am interested in finding the Fourier transform of y. So if I find the Fourier transform of y, if I just apply the definition is this summation goes from minus infinity to plus infinity, and then this is y of n, and then this is e raised to the power minus j omega n, right? And all I'm going to do now is just replace this y of n with the summation I have up above, right? So this is minus infinity plus infinity, and y of n is a summation k equals minus infinity to plus infinity x of k h of n minus k times e raised to power minus j omega n, right? So essentially, I mean, just note that this is actually y of n, right? This just goes here. Now I can play around with this summation. I can bring the k outside because everything is linear, and then have x of k here, the summation n on the inside, and I have this h of n minus k and e raised to power minus j omega n over here, right? And if you take a look at what this is, I mean, this is just the Fourier transform of h of n minus k, where k is the shifting. So you have shifted by k indices, and just just use the time shifting property to conclude that this is equal to summation k going from minus infinity to plus infinity x of k. I could use a change of variables as well, but I'm directly using this time shifting property. H of e raised by j omega times e raised to power minus j omega k, right? So this is h of e raised to power j omega times summation k going from minus infinity to plus infinity x of k e raised to power minus j omega k. So what do I have inside the summation now? So इस summation के अंदर क्या चीज़ है?
DTFT of the other signal.
The DTFT of the other signal, right? Excellent, right? So the DTFT of x, right? So this is just h of e raised by j omega times x of e raised by j omega, right? And this is y of e raised by j omega, right? So the convolution, so what we concluded is that convolution in the time domain is equivalent to multiplication in the frequency domain. And why is it important? It has, and what are the implications? The implications, once again, are in the frequency selective filtering, right? A frequency selective filtering application, and that's why, I mean, often you would see people use filters to just represent two LTI systems, right? They just say filters हैं. LTI, all LTI systems are actually filters. And the reason is because when you do convolution in time domain, multiplication may, there's this frequency domain where there's multiplication, and then multiplication leads to some sort of filtering operation. Some frequency components may be filtered out, and some frequency components may be passed through, right? As an example for that, um, I'm going to put up a video demonstration on LMS as well, with my own audio and some noise that you're going to see. And the idea is the following. The idea is that if you have an audio signal, right? The audio signal is a continuous signal that goes into an ADC, right, which is your sound card, which is recorded, right? And once it is recorded, when you take up the signal in MATLAB, that signal is a discrete time signal. It's just an array, right? And if you compute the Fourier transform of that array, that gives you an idea of what the Fourier or the frequency decomposition of your speech signal is, or my speech signal is, as you're going to see in the video demonstration, which I'm going to upload, right? So, for example, you may see that the speech signal has a Fourier transform which looks something like this. And let's say this is arbitrary, asal mein aisa nahi hota, right? But let's say this is a speech signal, or this is the Fourier transform of the desired signal. But then, as the example we did in the continuous time case as well, let's say there is some unwanted interference that reside here, and that reside here, right? And is symmetric on both sides, right? So this is this red thing is unwanted interference, and this would be pi, right? So everything is between pi and minus pi. So let's say this is pi and this is minus pi, and this blue thing is your desired signal. Now, if you want to extract this blue from everything else, right? So asal mein what you're hearing is this blue thing plus this red thing, right? What you're hearing is a composition, is a superposition of these two signals, which is not only contains the desired audio but also unwanted interference. And you want to extract this blue thing out from the superposition. Now, in the time domain, it's going to be very, very hard because I mean, they're just mixed on top of each other. There's no way for you to be able to separate them out in the time domain or visually see how do they separate out. But once you go into the frequency domain, it's clear that one of the signals has a frequency support which resides around 0, and the other one has a high frequency support, right? So you can extract the blue one out. How? How should I be able to? How would I be able to extract it out? Right. So a low pass filter.
So by using a low pass filter.
Exactly, a low pass filter. So I would use a low pass filter which has a cutoff. So this is something which I should use. So this cutoff should be omega c, and this is, let's say, omega minus omega c radians, and the height for this should be 1, right? So that's what I should use, and this is a low pass filter. Right? But this is all in the frequency domain. So because when and this low pass filter should be 0. This ideal low pass filter should be 0 for all other frequencies outside of this passband, right? Which is from minus omega c to plus omega c radians, right? And when in the frequency domain, I multiply everything with this green signal, clearly the red signal is going to be just canceled out because that's just multiplied by 0. And the blue signal is going to be passed through because that's multiplied by 1, right? And this is therefore an ideal low pass filter. So the ideal low pass filter has a frequency response which looks something like this. So the ideal low pass filter, if this is the frequency axis, So this is h of e raised to power j omega, and this is the ideal response. This is omega c, this is minus omega c, and of course everything is periodic, right? So the 2 pi पे दोबारा से repeat करेगा. All right. Now the question is, there must be a impulse response associated with it, right? So in order to determine the impulse response, what I am supposed to do is just find the inverse Fourier transform of this ideal low pass filter, right? So this is h of e raised to power j omega, and this is e raised to power j omega n times d omega, and this is just equal to 1 upon 2 pi. This is from minus omega c to plus omega c e raised to power j omega n times d omega. And I'm not going to go through the integration. We've done this quite a number of times. This turns out to be equal to sine omega c n divided by pi n. So this is the result that you get, right? So this is the impulse response of an ideal low pass filter, which has a cutoff frequency equal to omega c radians. And omega c, of course, is less than pi in this particular case, right? It must be less than pi for this to be a low pass filter. Now, what does this ideal low pass filter look like? What do you think? किसका होगा ये? So this is n. This is a sinc pulse, right? So, I mean, we're familiar with a continuous time sinc, and this is actually a continuous time sinc, except that continuous time sinc has been sampled at integer indices, right? So, the envelope is going to be a sinc. But what it is going to be are these samples, right? So this is what the filter is going to look like. And then just as discrete samples of the sinc pulse. And this is 0. And this is even, and this is real, and this extends infinitely in both directions. And that's why it is not a practical filter, right? Why is it not a practical filter? The reason why it's not a practical, the first and foremost, it extends infinitely in both directions. That's the biggest problem with this, right? Because if you were to do these calculations in a computer, I mean, you would have to have infinitely many calculations involved, and that's not feasible in a practical system. Okay, and moreover, you would have to have infinite memory, right? So you have to X को store करें infinitely memory looking into the past, and that's what you would need to compute the ideal low pass output. So this low pass filter is not practical, but from this we can derive practical filters as well. And the simplest one is just truncate this. अब ये say कि जी मैं यहाँ पे इसको ऐसे कि यहाँ पे truncate कर देता हूँ बस, और ये चलो यहाँ पे truncate कर देता हूँ, right? And I don't consider any samples. I'll start with this n max and minus n max. So this is an ideal low pass filter. Now, I'm going to come to this a little bit more, which is a moving average filter. But before I do that, जी उमर.
कैलकुलेशंस है वो अगर हमें फ्रीक्वेंसी डोमेन में करनी है तो फिर ये इंफिनिटी पे जाए तो हमें क्या फर्क पड़ता है?
Okay, good. Right. So the operation is always in the time domain, right? It's not in the frequency domain, right? So असल में क्या होगा? असल में ये होगा कि your signal, the time domain signal is going to come in, right? Which is the audio that I speak. I take a file, an audio file, and which is x of n, and from that and pass that file into a convolution block, which is an LTI filter, right? And if you use MATLAB, so you just use the conv command, and it will let you do those operations. Okay, and the output turns out to be y of n. right? So this operation has to be in the time domain, but the design perspective comes from the frequency domain. You get the point, Omar?
फ्रीक्वेंसी डोमेन सिर्फ थ्योरी बनाने के लिए प्रैक्टिकल में नहीं है.
So the frequency domain is only to help you designing this h of n, right? This h of n, the design for this actually comes from the frequency domain perspective. Because I know, okay, if I design my h of n to look something like this, which is a sync pulse, right, or the sample sync pulse, and then I pass my x of n into an LTI system, which has an impulse response equal to this h of n, what would happen is that all of the high frequency components are going to be cancelled out, and the low frequency components are going to be passed through, right? So all of this perspective actually comes from the Fourier domain, but the operations are being done in the time domain. Okay? Having said this, I mean, there are other nuances here, and I think that those are beyond the scope of this class. Okay, so I'm going to come back to this in a little bit, but and discuss some practical applications as well. But before I do that, let me do one particular example, which is the following. Let's say you have a signal x of n, and that signal x of n is passed through the following system. What the system does is it first of all multiplies this with minus 1 raised to power n, and then it passes through an LTI system, and then another multiplication with minus 1 raised to power n, and here this is an LTI, which has a impulse response h of n, and this has the same impulse response h of n. So they're essentially both the same LTI systems. And then what you do is you add them up, and you get y of n. Now, I can say something about what this LTI system is. This LTI system, this h of n, is actually an ideal low-pass filter. So this h of e raised by, so that's the information that's given to us, that h of e raised by j omega is an ideal low-pass filter with a cutoff equal to pi by 4 radians and minus pi by 4 radians. And I don't draw the periodic extension. I mean, that's implicit. Okay, so this is h of e raised by j omega. And the question is, what is the relationship between x of n and y of n, right? That's what we want to answer. And in particular, the question is, determine whether the system from x of n to y of n is LTI. And if it's LTI, so then determine the impulse response of the system. Now, you could go about this by going through the properties of the systems, but there's a much easier way, and that is to go through the Fourier or through the frequency domain, right? So what I'm going to do here is I'm going to define intermediate signals. Let's say there's this signal here is called W1 of n, and the signal here is called W2 of n, and let's say the one here is W3 of n, right? And I'm going to operate in the frequency domain, and because that's going to make my life easier. So पहले इस तरह कर लेते हैं कि I first of all figure out what is W1 of n as a function of x, right? So W1 of n is just minus 1 raised to power n times x of n, right? And this implies that in the frequency domain, W1 of e raised to power j omega, how is that going to be related to x of e raised to power j omega? क्या ख्याल है? So how is W1 of e raised by j omega related to x of e raised by j omega? mean, if I multiply by minus 1 raised to power n, what is that equivalent to? We did this in the last class. कौन थे last class में? Abdullah?
Sorry, sir, what?
Right, so minus, if I multiply a time domain signal with minus 1 raised to power n, what happens in the frequency domain?
It alternates.
It alternates in the time domain, right? But frequency domain में क्या होता है? Frequency domain में we talked about shifting, right? And shifting in the frequency by how much?
Yes.
So this is minus 1 raised to power n is just e raised to power j pi n. Right? So consequently, W1 of e raised to power j omega is just x of e raised to power j omega minus pi. Right? So these just shifted, the spectrum is shifted by pi radians, right? So the low frequency becomes, excellent Ibrahim, shift of pi, right? So the low frequency becomes high frequency, right? So 0 becomes pi, right? And pi becomes 2 pi, right? And low frequency becomes high frequency becomes low frequency, right? Now, what about W2 of e raised by j omega? W2 of e raised by j omega is just equal to x, so is equal to W1 of e raised by j omega times h of e raised by j omega. But W1 e raised by j omega, as I've just done above, is x j omega minus pi times h of e raised by j omega. Right? So that's W2. And what about W3? W3 raised by j omega, because there's once again multiplying with minus 1 raised to power n. So there's another shifting, right? So the shifting by pi, right? So this is just W3 is just W2 shifted by pi, right? And if I just plug everything in here, so this is h e raised by j omega minus pi, and this is x of e raised by j omega minus 2 pi, right? So, but this W3 is therefore h of e raised by j omega minus pi times x of e raised by j omega minus 2 pi. Omega minus 2 pi करने से क्या होगा?
x of e3 omega ही होगा।
You get the same signal back, right? Because it's periodicity in the frequency domain. So this is x of e raised by j omega. Because this is W3. And y of e raised by j omega, therefore, right, is just an addition of W3 and this is W4, right? Right. So this is, I'm skipping steps here. So this is h of e raised by j omega minus pi times x of e raised by j omega plus x of e raised by j omega times h of e raised by j omega. Right. So I have, what I've done is I've found a relationship between the input and the output. Right. So where the input is y, the input is x and the output is y, but that relationship is in the frequency domain. So that's a caveat, right? So all of these relationships are in the frequency domain. And the reason why I'm doing that is because they're much easier to handle, because convolution is just multiplication. Otherwise, I would have to have those summations, and those would have become very tedious, right? So all these are just multiplications. And I can simplify this even further. What I can say is this actually equal to x of e raised by j omega times h of e raised by j omega plus h of e raised by j omega minus pi. Right? So x of e raised by j omega is actually being multiplied by something, right? And that something is not that low pass filter anymore, right? But rather a modified filter, which I've modified through these special branching thing that you see in the system description, right? So the minus 1 is to power n, and then 2 branches, and then adding things up. That was a particular construction that I had. And from that construction, I've been able to derive the relationship between the output and the input is this, which is the output is equal to the input multiplied by this thing here, Now, given this, can I conclude that the system between X and Y is LTI? Anybody want to venture a guess? कि ये मुझसे मुझे पता चल सकता है नहीं चल सकता कि इन y और x के दरमियान में जो रिलेशनशिप है that is governed by an LTI system, right? So LTI systems, remember, systems are LTI if and only if the input and the output are governed by the convolution relationship. And I know that convolution is the same as multiplication in the frequency domain. So I know that convolution in the time domain is the same as multiplication in the frequency domain, right? And over here in the frequency domain, I do have multiplication. I do have multiplication of x with something which is a function of omega, right? There's no x involvement here. It's just something else, right? But which is a function of omega. And I can say that this is the equivalent frequency response of whatever the equivalent system is, right? This is H equivalent of e raised by j omega, right? And because of which I can conclude that y of n must be equal to x of n convolved with H equivalent of n, with this H equivalent of n is the inverse Fourier transform of H equivalent e raised by j omega. And that's from here, system must be LTI. So that's our conclusion. Now the question is, what kind of a system is it? I mean, what does it do to the signal? I mean, is it a low pass filter? Is it a high pass filter? Is it some other sort of a filter? So how do I do that, right? So in order to do that, I would need to try to see what is that equivalent frequency response that I'm getting, right? So if this is the omega axis, what is H equivalent, right? Ibrahim, what do you mean by an all pass filter? You're almost there, you're there, right? It's not necessarily an all pass filter, we're saying, right? So I can plot out the individual terms, right? So this is H of e raised by j omega, where this cutoff was pi by 4 and this cutoff was minus pi by 4, right? So this was H of e raised by j omega. And then there was this other term, which is H of e raised by j omega minus pi. Okay? So pi is just a shifted version of that, right? And ye cheez aayegi, where this is 5 pi by 4 and this is 3 pi by 4. And here's where pi by 2 is. And there's symmetry on both sides. So this is, if this is minus pi, so this is minus 3 pi by 4 and this is minus 5 pi by 4, right? So this is the H equivalent. So Ibrahim, is this a, no, okay, excellent, Masal. So this is a band stop filter. Excellent, because this is the band, right, which is stopped, right? So this is really a band stop filter or a stop band filter. And I have been able to achieve the functionality of a band stop filter by just using low pass filters, right? Those low pass filter use here with that modulation, with that minus 1 raised to power n thing, right? Which is a multiplication, right? It's only a multiplication, right? I use that in conjunction with two low pass filters and I add them very, very intelligently to be able to implement a band stop filter. Okay. But all of this analysis, I mean, I've been able to do this quickly and I've been able to do this easily is because of Fourier. It's because of Fourier analysis. But because otherwise I would have had to go into the time domain. Time domain mein convolution hai, and then things would have been very, very messy. It is possible. It would have been possible to still conclude that the system is LTI, but it would have been very, very messy. It's much cleaner way to do this is in the Fourier domain, right? So any questions about this example? Okay, so let me talk about something else, which is the moving average filter, right? Now, the way I'm going to motivate this is through this graph that you see on the screen. This is a graph I actually presented at E100 and some exercises for that. This is the last year COVID confirmed number of cases in Pakistan. So this is publicly available on the internet. You could just import it in MATLAB and sketch it out, right? But what you see is there this the and this is Umar. This is a discrete time signal, right? I would treat this as a discrete time signal where the indexes are here, even though my band, my label here is not exactly consistent with my mathematical definition. लेकिन आप just imagine कि यार ये 1 है, ये 0 है, ये 1 है, 2 है, 3 and all the way up to whatever the number of days was, right? So this is a discrete time signal, right? And this is actually a stem plot for that. Now, you see there are many missing values, right? So you see the number of confirmed cases at this particular date were zero. And this was zero here as well. And these are zero not because the number of cases were actually zero, but because this data was not reported, or at least the data that we had available with us, that did not include this particular information, right? Uske alawa, there some appears to be some outliers here, right? So, for example, this appears to be an outlier, right? So let me use another color, right? So this appears to be an outlier, right? Or this appears to be an outlier as well. मैं एक trend follow हो रहा है, trend follow हो रहा है, एकदम से spike आई है, and then the very next day it goes down, right? Which actually could have been because of the fact, I mean, if you really think about this could have been because of the fact कि अगले दिन zero थी, तो हो सकता है वो दोनों दिन की एक जगह पे आ गई हो data के अंदर, right? So there might be a data artifact, right? Now, one of the ways you would see, I mean, all the news reports that you see, I mean, they would have this, which is you see this raw curve, and then you have a 7-day average or a 5-day average or a 3-day average, right? Which is this blue curve here, right? So how do you compute this 7-day average? सबसे पहली बात ये है. And why do you compute the 7-day average? So that's the second point. So the first point is, if I can have somebody try to answer, okay, how do you compute the 7-day average? Let's say if you have that data available, this data available, और आपको कोई कहता है यार ये compute करके दो मुझे, तो what would you do? और चलें, why would you do it? चले पहले ये आंसर कर लेते हैं. Why would you do it? Any volunteers? Masna, you want to speak? You Masna, go ahead.
Sir, so that we can remove these outliers.
Yes, so we can remove these outliers, or another way to say put that is to get some sort of a smoothing.
Yes, sir.
Right, smoothing. A smooth curve को smooth करना आपने, right? And as we're going to try to link this, this is actually something in the frequency going on in the frequency domain. Okay? Smoothing, what it actually means is to get rid of the high frequency components and to retain the low frequency components, as we're going to see, right? So that's something we want to do. So do some smoothing. Now the next question is, how do you compute the 7-day average, a weekly average, जो भी कहते हैं उसे, but this is a 7-day running average. तो वो क्या ख्याल है, क्या करते हैं?
Sir, no idea इस बारे में भी.
Okay, so 7-day. Anybody else who has an idea कि मैं अगर आपको कहूँ यार डेटा रॉ दिया हुआ है, इसको स्मूथ करें through this 7-day average. तो मेरे पास आज का, जैसे let's say today is Saturday, right? And I have this raw data from the last Friday all the way up to this Saturday. So if I want to get an average or a weekly average क्या थी, so what I would do is I would take the past 7 days data and just average it out. And I say that my average today, or the running average today, is whatever that number was from the past 7 days. Okay? And kal Sunday aata hai, right? And then what do I do with the next Sunday? Next Sunday, from counting from that Sunday, right? Consider the past 7 days and compute the average for the past 7 days. And that's going to be your average. ठीक है, Monday, the past 7 days starting from Monday, and compute the average. So that's how you take the smoothing, right? So this is called a moving average filter, right? Or a running average, right? जी मसना.
सर सो इन शॉर्ट हम जो 7 days के केसेस हैं उनको ऐड करके डिवाइड बाय 7 करते हैं,
Yes.
which is like taking a mean.
Exactly, this is mean. This is the average. I mean, so I use mean is another is synonymous to average, right?
I thought कुछ थोड़ा सा ज़्यादा complicated हो.
No, it's as simple as that. As simple as that, right? But it's a running average, Masna. Right? That's
Yes,
important.
sir.
It's a running average. कि वो आप किसी दिन पे भी खड़े होते हैं तो उसके
Next
पास 7
7
डेज
days.
देखते हैं और अगले दिन पे जाते हैं तो आपकी वो डेज
Yes.
वैल्यू खत्म चेंज हो जाती है, राइट? स्लाइड कर जाती है, राइट? नाउ
Yes.
what I want to do is I want to put this mathematically, right? So let's say the Ross signal was Ross signal, let me denote that by x of n. And let me say that the smooth or the average signal, let me say that is y of n. How is y of n and x of n related to each other? Right? So this is where this mathematical visualization comes in. I mean, so I need to formulate this into something we're familiar with as a summation or an averaging or some convolution or some filtering, and that's where we're headed, right? So the first thing I want to do is, yeah, how is y of n going to be related to x of n? Right? Any ideas? कोई mathematically इसको formulate कर सकता है?
accumulation property जो पड़ी थी उससे कुछ.
Yeah, so abhi tak, the way I'm going to do this is not talk about convolution yet, and just talk about it's common sense.
The convolution नहीं, accumulation जो थी integration
Accumulation, good.
Yes, sir.
Lekin accumulation is not from minus infinity to the current time, right?
और n से n plus 7 तक कर देंगे, n minus 7 से n तक.
Exactly. Ibrahim, you want to say something?
सर आई थिंक accumulation के साथ साथ कुछ filtering भी करनी पड़ेगी साथ.
All right, filtering से क्या मुराद है?
सर ये जो बीच में वो आ रहे हैं हाई फ्रीक्वेंसी बहुत स्पाइक्स ही आ रही हैं तो उनको निकालने के लिए शायद.
Right. So वो spikes आप देखेंगे सिर्फ averaging से निकल जाते हैं, right? And all I've done, and this is actually something I've done myself, right? So all I've done in this blue curve is just the averaging, nothing else, right? So if I were to write this mathematically, this is what I would do. And sort of Umar, I think, gave me that idea, which was, okay, agar main ye kar दूं 1/7, right? And then I have a summation, and this is this summation, x of n minus k, and k goes from 0 to 6, right? तो ये असल में क्या करा होगा? This would be taking at any time, at any particular day, y of n, this would be the x of n, or x of n minus 1, plus x of n minus 2, x of n minus 3, x of n minus 4, x of 5, and 6, that which is basically the past 7 days, right, including the present, right? So past 6 days and the present, right? And that's divided by 7, that's just like taking the average, right? So this is the mathematical relationship between y and x. And actually, this is what I just implement in this blue curve, right? But here's the interesting point. This is actually nothing but convolution, right? And or this system, you can easily prove that this system is LTI. First off, this is a system, right? Because this has an input signal and this has an output signal. If this is an input signal, there's an output signal, that means this must be a system, right? It turns out, and let you just take my word for this, that this system is LTI. It's linear, and it's time invariant. If it's LTI, can we determine the impulse response for this system? How do I determine the impulse response? अच्छा, इसको मैं let me generalize this a little bit as well and say कि जी अगर मैं if I say कि जी m day moving average. So I'm no longer talking about m equals 7. I mean, this could be m equals 3, m equals 5. And then the generalized relationship would just be y of n is equal to 1 upon m, k equals 0, all the way up to m minus 1, x of n minus k. Right? And for m, you could choose m equals 7, you could choose m equals 3. I mean, often in news articles, 3-day average compute kar rahe hote hain, right? Right. Excellent, Masna. Slight bit of an issue. N minus 6.
7 होगा.
7 hoga. Excellent. U of n minus. Chalo. Excellent. But how did you go about this, Masna? Kisa nikala?
Because I knew that age of n was just changing the limits of the summation.
Good.
Because बाकी x of n minus k जो है वो तो होता है convolution के अंदर.
Good. Excellent. Excellent. Right. So that's one way to do it. I would do it another way and say, Kiji, in order to determine the impulse response, I just do what? Just plug in x of n equals delta of n. Right? Because impulse response is defined as what? Impulse response is defined as the output that you get when the input is the impulse, is the unit impulse. And from here, I obtain that h of n is equal to 1 upon m summation k equals 0 to m minus 1 and delta n minus k. And clearly, I mean, this is a train of impulses, okay? And you can see that this is actually 1 upon m u of n minus u of n minus m m hoga, yeah, u n minus m, exactly. Right, so this is the impulse response is just these ones which start at 0, okay? And dot all the way up to m minus 1. And this is the impulse response. Now, what we're really interested in finding now is, because we're talking about convolution property, is, I mean, how does this do the smoothing? Or for that matter, let me get some intuitive insights from you. I mean, what would you expect if this capital M was very large or very small? And अगर मैं इसको ज़्यादा करूं या कम करूं, I mean, what kind of behavior would you expect? So if this is a 7-day average, if I compute the 30-day average, so what would you expect the blue thing to look like? Ji Ibrahim.
Sir, I think smoothness increase होती जाएगी जैसे
Smoothness increase होती जाएगी, right? Exactly, smoothness increase होती जाएगी. Or actually, smoothness may go to a level where the 30-day average may not be telling you information about the high frequency things, because हो सकता है वो weeks के हिसाब से कि number of cases change हो रहे होते हैं, लेकिन वो 30 days just the entire month average out together. तो आपको ये पूरा का पूरा ये trend इस तरह का ना नजर आ रहा होता, हो सकता है वो this might be just something like this, right? Or for that matter, if this is even larger, if this is even larger, as Asad points out, okay, I mean, this would get smoother and smoother and smoother, right? As opposed to this, if m was very, very small, right, you would expect those sharp edges or sharp, these to be even sharper, okay, और भी ज़्यादा sharp हो जाएंगे, right? And this is what our intuition tells us. And let's try to see here, I mean, how is it related to Fourier transform, right? In order to relate this to Fourier transform, I would have to compute, or the convolution property, or the filtering phenomena. I would have to compute the Fourier transform of h of e by j omega, right? So this is equal to 1 upon m summation. And this is n equals 0 to m minus 1. And this is e raised to power minus j omega n, right? I've skipped a step. That step is h of n I know is equal to 1 only for the values of n which are from 0 to m minus 1, and all other values are 0. So इसलिए I've just skipped a step, right? What is this equal to? I just apply the finite sum formula that we're familiar with. This is equal to e raised by 1 minus e raised by j omega times capital M divided by 1 minus e raised to power minus j omega. And can I simplify this further? Yes, I can simplify this further. In a similar way, we've run a similar example here. And what I would do is I play a trick where, sorry, this is minus. I just take e raised by j omega m by 2 as a common factor outside. And this becomes e raised by j omega capital M by 2 minus e raised to power minus j omega m by 2. And in the denominator, I am going to take e raised by j omega by minus omega by 2 as a common factor. So this is e raised by j plus omega by 2 minus e raised by minus j minus omega by 2, right? So then what do I get? So this is 1 upon m, and then this is e raised to power minus j omega by 2, and this is m plus 1 and minus 1. Right, so this is just an exponential. And what I have in the numerator divided by denominator, this is just sine omega m by 2 divided by sine omega by 2. Right, so this is my frequency response of the moving average filter when I take that m day average, right? Let me try to sketch this out, and by sketching it out, things are going to come clear. What happens when m increases, what happens when m decreases, right? So, and in particular, what I'm going to plot or sketch is the magnitude of h of e raised by j omega. Yeah, chale, just this term. I wouldn't say the magnitude. Okay, so magnitude karte hain, right? So the magnitude of h of e raised by j omega, right? Now the magnitude, when I take the magnitude may this term just goes away because the absolute value for this is just 1. And all I'm going to be sketching is just this thing here, the absolute value of this thing here, right? And chalo, let me pull this down and do some more analysis. Okay. So the absolute value of h of e raised by j omega is equal to 1 upon m, and then absolute value sine omega m by 2 divided by sine omega by 2. Now here's the question. So I can take my word for this. This is going to be a decaying slightly and then is periodic. But the question is, where are the zero crossings for this, right? So zero crossings occur when omega times m divided by 2 is any integer multiple of pi, because sine always crosses a 0 whenever the angle is either pi or the argument is pi or the argument is 2 pi, right? It's a multiple of pi, right? Any integer multiple of pi. That's where the zero crossing is going to be. And from here, I conclude that the zero crossings are going to be for all values of omega, which are equal to an integer multiple of 2 pi divided by m. Right? Now, here's what the sketch is going to look like. And let me just plot the sketch for omega equals, for m equals 5. That's 5-day average. So this has to be symmetric. So this and this and this. So this is 0. This is 2 pi by 5. This is 4 pi by 5. This is 6 pi by 5. This is 8 pi by 5. And this is 2 pi, which is 10 pi by 5, right? And pi would be around here, right? So this particular sketch that you see is for m equals 5, right? Do you observe what kind of a filter this is? This moving average filter? I mean, is this a low pass filter? Is this a high pass filter? What kind of a filter is it? Right? It's main lobe, which is, and the height here is actually 1. That's something you can show. The height here is 1, right? Now, the highest peak is at omega equals 0. And the main lobe, which has the highest energy, which is this lobe here, right? This has a cutoff at 2 pi by 5 and in 2 pi by m in general, right? Maybe screen. Give me a minute. All right, so what kind of a filter is it? It's clearly a low pass filter. I mean, it's not an ideal low pass filter. I mean, that's for sure. But it is a sort of a low pass filter, right? And it's the simplest low pass filter that you can think of. And this is the moving average filter. This is called the moving average filter, right? And the reason why it's called a low is it's a low. The reason why it is a low pass filter is because the highest energy or the highest frequencies that are going to be let through reside in the low frequencies. And it's clearly, this is why the signal becomes smooth, because the low frequencies are passed through and the high frequencies, when you do that averaging, are just canceled out or mitigated, right? Now, the question is, what happens if I increase M, right? I mean, if I move from 5-day average to, let's say, 14-day average, a 2-week average, right? So what would you expect if I increase M?
So the width of the low pass decreases
Decreases,
because
exactly, right?
it becomes 2 pi over 14, which is
Excellent,
pi over 7.
excellent, excellent. So as M increases, so the cutoff decreases, right? And that is why you would observe the signal to be even smoother when M increases, because the cutoff is going to decrease, right? And the even smaller frequencies, so I mean, the amount of frequencies that are being let through are now going to be of very small frequencies. उससे ज़्यादा high frequency components सारे के सारे, they're going to be cancelled out, right? So what we know from intuition or practice, we've been able to make a connection of it to this rigorous analysis that comes from this Fourier perspective. Okay? And from this, you can make others. So how do you choose M, right? This would give you another perspective. This Fourier domain would give you a perspective कि M किस तरह का होना चाहिए. अगर M बहुत ज़्यादा करते हैं तो क्या होगा? M बहुत कम करते हैं तो क्या होगा? What's just the right value for M, right? Okay. Any questions about this moving average filter? Okay, so I'm gonna stop here. There's one other property that I wanted to do. I think I'm gonna skip that, or skip. Let me just mention that in passing. I think I missed it out, which was the Parseval's relationship. So I'm just gonna list this without an example. And as you can imagine, this just says the energy in the time domain and going from minus infinity to plus infinity is equal to 1 upon 2 pi integral x of e raised to power j omega absolute squared times d omega. And this is the energy. And since this gives you the energy, this thing here, which is x of e raised to power j omega absolute squared, is often called the energy spectrum, just like in the continuous time domain. Energy spectrum density. I mean, which is exactly what we defined when we're talking about CTFT as well. Okay, so this is where I will end. Any questions?